Doing a lot of straight chain alkane examples where we've got a long chain of carbons with either hydrogens all around or some other type of kind of constituent or substituent group on there. But we could also, if we want, take those two carbons on the end, and if the chain is long enough, bring them all the way around and hook them up to make a cyclic or a cycloalkane. Nomenclature rules stay the same. We're just going to add the prefix cyclo to indicate that it's formed a ring, and if there's any special groups coming off of it, then we would go ahead and we would number those groups. One of the most common naturally occurring cyclic structure is one that looks like this. We would then have technically two hydrogens coming off of each of these as we're looking at our cycle or our cyclic structure. But we've got, if we're just counting our carbons, we've got 1, 2, 3, 4, 5, 6 carbons going around, so that would be a hexane. This would be hexane. But to show that it is in a ring formation, we call it cyclohexane. And so this would be a cyclohexane. If we wanted to do the skeletal form for this, we just make a hexagon, and this would be what we'd call a cycloalkane cyclic hydrocarbon. If we had one of these that had a special group coming off of it, so say this was a bromine coming off on this side here, we would have to show that that is on our cyclic structure somehow. Since this is a ring, we can start numbering wherever we want. So we're going to number that right there on the one position. This is 1 bromo cyclohexane. But do you really need that? If it's a ring and you only have one group on there, you could arguably just say it is a bromo cyclohexane. It isn't until you add a second one on here, so say we had a chlorine over here, now we would have to number in order of preferential placement as to where those two are relative to each other. We're always going to number in lowest values or lowest sum. If we called this our 1 carbon, this would then be our 2 carbon. Now we have 1 bromo, 2 chloro, cyclohexane. Oops, sorry, my L keeps ending up in the wrong spot. Hexane. In terms of who gets priority here, technically that comes back to reactivity. We're not going to stress that so long as they are relative to each other. Whether you numbered this one and this 2 or this 2 and this one, the distance between them ends up actually being the same. And so you would end up back with the same structure. And so we're really just getting it so that whatever we wrote here for our IUPAC, or International Union of Pure and Applied Chemistry, this would get us back to the structure, or from structure back to the name. So for example, if I had 1,3 dichlorocyclobutane. Holy buckets, that's a mouthful. But the name is set up in such a way that you should be able to draw a reasonable and repeatable structure for this IUPAC naming system. We've got a cyclobutane, butane meaning 4 carbons, cyclo meaning that they're in a ring. I'm going to do the skeletal form just to kind of hook them together. Ends up as a box, but 4 carbons attached, going to make a box. We've got 1, 3. Okay, I'm going to call this 1, 2, 3, 4. I'm just numbering around my ring, so to speak. I got a 1 and a 3. Dichloro. Oh, they're both chlorines. And so this would be 1, 3 dichlorocyclobutane. So it's a nice, real easy way to start to kind of identify these cyclic structures. Let's do one more going from the name back to the structure, just because I think that's a good way to look at some examples. Let's do 1, 4. Oh, nope, sorry. Let's do 1 methyl. Nope, 1 chloral. Sorry. 4 methyl cycloheptane. Sure, just to really make this awkward. Heptane being 7. So we need 7 carbons. 1, 2, 3, 4, 5, 6, 7. That looks a little funny. It's almost like it doesn't appear very often in nature because it looks kind of funny. That's a different thing. Cool. I'm just going to assign my 1 position at some point on the ring. I'm going to call this 1, 2, 3, 4, 5, 6, 7 going around. I've got 1 chloro. Here's my chlorine. 2, 3, 4 methyl. Well, remember that just the line implies a carbon. This would then we would assume to be saturated with hydrogens. This would be my structure for 1 chloro 4 methyl cycloheptane for our cyclic alkane structures. Cool. I just want to give you some examples on our cyclic structures. Again, because these end up locking into position, these end up giving us slightly higher melting and boiling temperatures. We talked about that earlier, but good to kind of come back and talk about those cyclic structures.